Hello class, and welcome to week 8. Last week we are still on chapter 8, which is differential and multi-stage amplifiers, and last week last week 7 according to my schedule, we looked at item 1 or topic 1 and topic 2 and a little bit of topic 3 from chapter 8 already, right? We were introduced to the mass differential pair. We looked at the small signal operation of the mass differential pair, and also we used the same ideas to study BJT differential pair. Then there is a topic in the middle, other non-ideal characteristics of the differential amplifier. This I'm going to skip for the moment. If it's necessary, we'll come back and look at some of the stuff in it. But this week I want to do in day 1 the differential amplifier with active load, which is topic 5, and then in the next set of recordings, next 2 recordings, we'll look at the last item and last topic in chapter 8, which is multi-stage amplifiers. Okay, so that's the plan for this week, and with that we should be able to complete chapter 8, which is differential and multi-stage amplifiers. So let me skip to the first slide of this topic 5, which is I think slide 47, 48. Yeah, slide 48 is the first slide of 8.5, which is a differential amplifier with active load. So it's called active load, and it's also sometimes referred to as current source load. So don't get too confused. It means the same thing. So under 8.5 in this recording, we have again 5 topics: 5.1, 5.2, 5.3, 5.4, and 5.5. So we'll look at each one in detail. Okay. Again, this recording I'll cover the theory of all of this, and the next recording we'll look at the examples, numericals also related to these topics. Alright, so I borrowed a slide from the earlier material of this same PowerPoint, which is 8.1. So we were introduced to the mass differential pair, and we saw that there are 2 transistors, Q1 and Q2, and each one has a signal in the input side. So assuming this is a common source configuration, your input signal is applied between the gate and the common source. The output is taken between the drain and the gate, right? So that's the basic configuration, and we spent a lot of time understanding differential input, common mode input, and all that. So yeah, nothing more I want to say there. On this slide, here I'm showing you a BJT differential amplifier. The ideas are the same for MOS and BJT. We learned that you can take the output differentially. That means the output is taken between the 2 drains or the 2 collectors in this case, if it's a BJT. So the output VOD, the output signal voltage, is VO2 minus VO1, right? Single-endedly means the output is taken between a drain and ground. That means either VO1 or VO2 can serve as the output, if we are interested in taking it single-handedly. So this stuff also we have studied, and we know the advantages of taking it differentially is that the gain is double. It's higher by a factor of 2 compared to the single-handed. Secondly, it increases the common mode rejection ratio, CMRR, is higher if you take it differentially. So these are the two benefits of taking the output differentially. Excuse me. Now, before we talk a little about the actual topic, which is having a current source in the output circuit or the drain circuit, we are talking just a little longer about single-handed and or taking the output differentially or taking it single-handedly for a specific reason. And the reason is, as shown here, you have a 3-stage amplifier, stage 1, A1, A2, A3. A1 and A2 are differential in, differential out is what he calls it, and they have gains of A1 and A2. But the last stage, A3, is differential in and single-handed out, right? A3 is being taken with reference to ground from one output. So the point he's making is, in any such amplifier with many stages, and obviously we'll study multi-stage amplifiers in the next lesson, but almost always it is usually required at some point to convert the signal from differential to single-handed. So you cannot avoid having to take an output as a single-handed output at some point in a multi-stage amplifier. So will you get the benefits, or will you lose the benefits of taking an output as a differential output for A3 stage, or is there a way we can prevent it, or is there a way we can avoid the disadvantages? So that's what we'll study. So if you want to convert to a single-ended output, the simplest method is shown here, and he calls it a simple but inefficient approach for differential to single-ended conversion. Okay, this method is always possible, but inefficient meaning not so good. So what is this simple method? You just ignore the drain current signal of Q1, right? So if you have Q1 here, you just ignore whatever is going on here, take out the RD in this circuit attached to Q1, and just focus on taking the VO from the output drain of Q2. So ignore the drain current signal of Q1 and eliminate its drain resistor altogether. The disadvantage obviously is we lose a factor of 2 or 6 decibel in the gain. So gain is only half of what you can otherwise get, as a result of wasting the drain signal current of Q1. So Q1, even though the current exists, you're kind of not using it, so you're wasting it, right? So this is the simple method. Now obviously when he gives you a simple method, you know that it will be followed by a complicated method, and the complicated method will hopefully help us get rid of the disadvantage. Okay? Alright. So now we finally come to the main topic, which is the using an active load. So if you compare this to this on slide 50 or slide 49, you see these two resistors in the drain, right? So going back to slide 52, the two resistors in the drain are now removed and replaced by a pair of transistors Q1 and Q2, Q3 and Q4. Q1 and Q2 is the differential amplifier, Q3, Q4 is the current source load. Also in this case is a current mirror. You know, a mirror is formed by connecting these two gates like this. If you do that, it's a current mirror. And we have studied current mirrors. If you don't remember, please go back and look at my notes from the previous chapter 7, I think is where we studied current mirrors and current steering and all that. But if you put a pair of transistors Q3 and Q4, and remember these have to be opposite, right? If this is NMOS, these current mirror transistors are PMOS. So a current mirror transistor pair is used instead of the drain resistors, RDs. So the differential pair formed by transistors Q1 and Q2 is loaded by a current mirror formed by transistors Q3 and Q4. Because of the current mirror action, it is possible to convert the signal to single-ended form, that is between the output node and ground. Now we are talking about the output signal, right? I should probably say the output signal to single-ended form. That is taking it between the output node, one node, VO, and ground with no loss of gain. That's the important thing to focus on. So previously we kept thinking we're going to lose gain, but the advantage of having Q3 and Q4, two advantages. If you're doing this on an IC, you know that resistors are hard to do on an IC. It's easier to do Q3 transistors, Q3 and Q4. That's one advantage. And the other advantage is you don't even need to lose the gain. Okay, so that's the big benefit from using an active load. Okay, so in this drawing, let me move this, figure 832, he shows a lot of analysis to prove to us why the gain is not lost. So here B, or figure B of figure 832 is an equilibrium condition, assuming everything is matched, Q1, Q2 are matched, Q3, Q4 are matched, and the input signal is just ground, no input signal. You can say that this bias current I, which is coming from a current source, that flows into the two branches equally, I by 2 and I by 2. And the V output is VDD minus SG3, right? This, whatever is the signal, that's the output. So now in figure C, if you apply some input voltage symmetrically, some input signal symmetrically, half here and half here, then what happens? Now you'll see that this output lead has a current 2I coming out of it, because two currents each of I magnitude are coming in to this node. Okay, so let me move on to the next slide where we have a little more description. So on slide 54, he explains what exactly is going on with the input signal VID, right? Differential input signal VID is applied. Instead of the drain resistors R3, R4, we have a current mirror. So the operation of this circuit with 4 transistors is like this. With a differential signal input Vid applied as shown, transistor Q1 will conduct a drain signal current I equals GM1 Vid by 2, right? Remember, this is the transconductance, which is the opposite of resistance, right? Resistance is V by I. Conductance is I by V. So you take an I, divide by V, multiply by V, so the V's go away. So what you're left is a current value. So that current value I is shown in Q1. So the transistor Q1 will conduct a drain signal current, right? This is signal, not bias at all. It's not connected to the big I, this is a small I. And that I value is this. Similarly, transistor 2 will conduct an equal but opposite current. So this current I goes to ground and this current I comes from ground in Q2. The values are the same, and this current I, because it's also the current here, and if Q3 and Q4 are matched and they form a current mirror, you know that this current, reference current, is also shown here, is reflected here, right? It's the mirror of this I. Now, if Q3 and Q4 have the same W by L ratios, then we know that this I and this I are the same. If the W by L ratios are different, then of course the formula gives us this I as a function of this I. But in this case, let's assume Q3, Q4 have the same W by L or the same GMs. Then the two currents are the same. That's what he explains here. The drain signal current I of Q1 is fed to the input of the Q3, Q4 mirror, right? This Q3, Q4 mirror has this input point, which is this point between the two gates. So that I flows into it, which responds by providing a replica in the drain of Q4. Replica means a duplicate, exact same thing. So in the drain of Q4, you have another I. So at the output node, we have two currents at this node, each equal to I, which sum together to provide an output current of 2I. So it is this factor of 2 that ensures no loss of gain, even though the output is taken in a single-ended manner. So even though you are taking the output VO as only VO with respect to ground and not as the differential V or D, you still get the full gain because this circuit is able to give you twice the current into the load. Okay? So that is the logic that tells us that the output voltage, the output signal, the gain that you get from the transistor from this combination, the gain of even the single-ended output is the same as the gain if you had taken the signal differentially. If you had taken the output differentially or if you take it single-endedly, the gain is not reduced, it still stays the same. Okay? Alright, so that's the reason why, that's one of the benefits of having a current source load on the output, on the drains of the two transistors of the differential pair, instead of having just resistors, RDs, in the drain circuit. Okay. Alright, so now we move on to, so we looked at 8.5.2 so far. We learned that the gain can still be saved, still have a higher gain. Now we need to find, in 8.5.3, we'll find the differential gain of the active loaded MOS pair. Okay, now you can still take the output single-handedly, no problem. But when we say differential gain, don't get confused. What it means is the gain for differentially inputted signals. That means the signals are coming in to Q1 and Q2 in a differential manner, right? So what that means is they come in like this, VID and minus VID. If such is the case and you're taking the output single-handedly, or you can take it differentially also, doesn't matter, but we are more focused on taking it single-handedly in some of these formulas here. What is that gain? So to help us with that, to do the analysis, we first start by creating a model of our differential amplifier, a very simple model, right? There is an input VID somewhere here, and in our this blue stuff is the differential amplifier, right? With the whole Q1, Q2, Q3, Q4, everything together. So whatever is the input, it first gets converted into, in this model, into a current source, a dependent current source. And what is the value of that current? It's this transconductance, a capital GM, multiplied by the input voltage, the differential input voltage. And then you always have an output resistance that you have to worry about. Sometimes you don't have to worry, you can think this is infinite and leave it open. But generally it benefits us to have a current flow through a resistor, and that gives you a signal voltage at the output VO. So a simple model. Now we have to find what this GM is, right? Everything else we know, or we have to find the GM and the RO, right? So the calculation of the derivation of this is in the textbook. There's a lot of steps involved. I advise you to look through it at least once so that you understand how the derivation proceeds. But for our purposes, I won't have too much time to go through it. I mean, here is a drawing that is used quite a bit. First of all, you have to find GM, then you have to find RO, right? These two parameters. So this circuit, for example, tells you how to find RO, which is this output resistance looking into the circuit into Q2, the output transistor, from which we are taking the output signal VO. To find this, he connects a dummy voltage Vx and then finds RO as the ratio of the dummy voltage divided by the dummy current, and that gives you RO. Okay. So after a lot of analysis, he comes up with a simple result that we like, that RO is nothing but RO2 in parallel with RO4. What is RO2 and RO4? They are the intrinsic output resistances of these two transistors, Q2 and Q4, right? We know they depend on like the early voltage and so on, but you can see RO is shown here, RO2 is shown here, and RO4 is shown here. These come from the small signal modeling of the MOSFETs, both the NMOS and the PMOS. So those ROs, if you put them in parallel, you get the output resistance of this model. Similarly, the transconductance, the overall short circuit transconductance, capital GM, is nothing but GM of 1 and 2, these two devices Q1 and Q2, whatever their GMs are, and you know their GMs can be calculated like this. And so this capital GM is nothing but small gm. Now to find this GM and to find this RO, lots and lots of steps are involved. Take a minute to understand. I mean, mostly he just uses KCL, KVL at different points in the circuit. And then I notice that he will say certain resistances are pretty high, so we can ignore them. So using a lot of ignoring and some KCL, KVL type analysis, we end up with these formulas for GM and RO. Then the gain, the differential gain, that is the ratio of the output voltage to the input voltage, or rather the ratio of the output signal voltage to the input signal voltage, which is VO by VID, is GM-RO, right? It's just GM times RO that gives you the gain, and that is nothing but GM into RO2 in parallel with RO4. Okay. Another way of saying AD, the differential gain, is the intrinsic gain AO, which is GM-RO divided by 2. So if you don't want to mess with, and again we keep using as examples the fact that all these transistors are matched. That means their GMs and their ROs are pretty much identical. If that's the case, then AD is nothing but A0 by 2 or AO by 2, where AO is the intrinsic gain of the current source loaded differential amplifier, or you use this formula AD, differential gain, is GM times RO2 in parallel with RO4. Okay. So I've summarized like 4 or 5 pages of derivations in the textbook into the simple formulas that we can use for solving problems. So that's 8.5.3. The next thing he wants us to do in 8.5.4 is to similarly derive common mode gain and then CMRR. Now you know common mode gain is the gain of signals that are on both the inputs or both Q1 and Q2. It's generally undesirable. You don't want any common mode gain. You want common mode gain to be 0, right? So that CMRR is very high. You can say the differential amplifier rejects common mode signals, and you have CMRR of infinity, very high. But in reality, the common mode gain is not quite 0. It doesn't entirely reject common mode signals. There is some gain. So again, to find what common mode gain is in this circuit, right, you can see how common mode gain input signal is shown. The same value is shown in both cases, but we want it to be rejected, right? And what is the value of that gain? He goes through again a lot of analysis, both of the differential transistors and the current mirror transistors, and he comes up with this formula for the output as a function of the input. So if ICM is the common mode signal, first of all, here's an explanation for why we even have any common mode gain. Finite value. Why is it not 0? The finite common mode gain is due to the current transmission error introduced by the current mirror load. That is due to the finite value of RO3. If you didn't have any RO3, if it was infinity, then you would not have any common mode gain. And then you can say the CMRR is infinity. The problem is there is always going to be some RO3, which is also the same as RO4. And because you have some RO3, you're going to have some common mode gain. That means the amplifier will try to amplify common mode noise even though you don't want it, right? So this complex formula, you can read how he does it. Look at all the steps, all the parameters here. There is an RSS, and what is RSS? RSS is the output resistance of the bias current source. Remember, there's always an I current source here, right? And that I has its own resistance, which in the small signal model we have taken all that out, the biasing stuff we have taken out. So you're left with this RSS here. Then you have these intrinsic resistances, output resistances of Q1, Q2, Q3, Q4, which is called small r O1, O2, O3 and O4. So those come into the formula here. Then you have this RO1 and RO2 that comes into the formula. And what is RO1 and RO2? You can see it on the previous slide. It is the output resistances as shown in the small signal models of the two differential transistors Q1 and Q2. So there's an RO1 and an RO2. So all these things, all these values enter the formula. Now luckily he tells us that you can neglect RO1 and RO2 because RO2 is generally very high in this formula, and you're taking a very high and paralleling it with a very low. You can forget about the very high. No current will flow through the very high. All the current will flow into the parallel branch with the very low. We know that. So this formula, you can neglect these big R's. Also these two GMs, GM3 and GM4, which are the GMs of these, are pretty much identical. So luckily this huge formula can be reduced to VO by VICM, that is the output, by the input common mode signal to get this simple formula. This can again be simplified apparently because the RO3 and RO4s are the same, and this factor GM RO3 is much greater than 1. That means this goes away. So you end up with a pretty simple A common mode gain due to common mode signals as 1 by 2 GM3 RSS. Okay. So this formula is what we use a lot in problems. So make sure you understand this. Now we did bring in a new factor RSS, which is here, which is generally given. If not, you can also calculate it. But now we see that ACM has a simple form. Okay. Once we know the two gains, the differential gain or the gain for input signals applied differentially divided by the gain for input signal applied as common mode. That ratio we know is CMRR, and so that formula becomes this. You can do this, or if you can even further simplify, it has this simple form GMRO times GMRSS. Okay? And what is RO? The intrinsic output resistance is nothing but RO2, RO4. We assume they are the same. And you come up with a formula for CMRR. Okay? So, in this section then, up to 8.5.4, for MOS devices, we have studied how we can take the resistors out from the drain circuits, put a pair of PMOS transistors in a current mirror type configuration. Thus, you save the loss of gain. Normally, gain would fall by 2 if you took the output single-endedly, but by having this current mirror load, we don't lose the gain. Next, we calculated gain AD when the inputs are differential, meaning the signal. We also calculated the gain when the inputs are common mode, which is noise generally. And then we said for such a configuration, for this configuration, the common mode rejection ratio has a formula which we derived, or he derived in the textbook, as a ratio of AD by ACM. So those are the 3 or 4 important things we finished in 8.5.4, up to 8.5.4. Okay, so we have some examples and numericals. We'll come back. There's a couple more steps in theory that I need to quickly address. Now, in the last chapter, chapter 7, which was all about building blocks of IC circuits, there was a section at the end, 7.5, which I think I didn't do I think I added some slides in the PPT, but I may have missed talking about it in my lecture, in my recording. So, I want you to go back and look at it if you haven't already. It's not very difficult concepts. All it tells us in 7.5 is that you can do some improvements. What is the improvements? You get better accuracy of the current transfer ratio of the mirror, and you get higher output resistance of the current source RO. So RO can be made higher by using some modifications to our cascode mirrors that we studied. Generally, MOS mirrors, if you can cascode them, you get some benefits, right? Cascoding improves the output resistance of the current source, and if it's a BJT, then it also improves the betas, the gains. So we didn't. I want you to just go back and quickly go through those slides. But one slide here is important, which is 7.5.4, which is something called the Wilson mirror, the Wilson MOS mirror. So let me quickly do that one thing here, and then we'll finish this chapter by looking at BJT version of the same thing. So this is a basic MOSFET current mirror, right? You know this. If you have a I reference, the output current will be connected to the I reference by this formula, and if the W by L's are the same for the two, Q1, Q2, then the I output equals the I reference, right? Also, the output resistance is RO2, which is the intrinsic output resistance of Q2. Now to this arrangement, if you add either a transistor here, an identical transistor, or if you add two transistors, both Q3 and Q4 are added to Q1 and Q2. Now remember, all this is only for the current mirror, the load, not to the differential amplifier. We are not talking about that yet. Such an arrangement is called a current Wilson MOS mirror. Wilson is the guy that invented it. And so the advantage of the Wilson MOS mirror is that it increases the output resistance by this factor. So previously, if the output resistance was only RO2, now the output resistance becomes GM3 RO3 times RO2. So this factor in brackets, GM3 RO3, is how much additional output resistance you get by having these extra transistors in the circuit for the current mirror. Why does this help us here? To obtain a large CMRR, the circuit implementing the bias current source should have a large output resistance. So this is possible with a Wilson current mirror. So anytime you have a current mirror, if you are able to increase its output resistance, you get a better CMRR, a larger CMRR. And we know we like large CMRR compared to small CMRR because that means the differential amplifier is more immune to common mode signals. So one of the benefits, one of the ways to have a high output resistance is by putting in a Wilson mirror instead of a regular mirror. Okay? And we'll do a problem here, and that's why I had to teach you Wilson mirror as part of my lecture. So when we look at the problem, we'll understand better why the Wilson mirror is helpful. Alright, with that there are some more problems, but problems which we look at in my next recording. For now, I will come to the very last topic of interest here, which is 8.5.5. Here we talk about the bipolar differential pair with active load. So this is not MOS anymore. Here we have NPN transistors. Same concept. Instead of having collector resistances, we put a current mirror consisting of two PNP transistors, Q3 and Q4. So these are NPN, this is PNP. We still have a constant current source for biasing I, and then we have VEE on the emitter side, and instead of VDD we have VCC here, right? So the same logic holds as what we studied for MOS. Again, we need to find CMRR, but to find CMRR we first have to find AD, or a formula for AD. And the formula for AD, same logic, a capital GM into RO, and that becomes GM, small gm. RO is RO2, RO4 in parallel, this RO2, RO4, and you get the differential gain. Similar compared to what we studied already, the common mode gain has a formula. It's this. It's written in terms of beta. You know, transistors, BJTs have beta. And then there is an RE, which is the output resistance. So common mode gain has this formula, and then CMRR similarly has this formula. Okay. So after this I have some numerical examples on BJTs with active load, but the derivation and all this again is in the textbook. I don't want to go into it, but the formulas are all here. And the logic is exactly the same as what he did for MOS for BJT circuits. So I'll stop here. When we come back, we will look at problems both for the MOS differential pair with active load and the bipolar differential pair with active load. Okay.